In this video, we'll cover the problem Course Schedule 2. So here, we have a number of courses we want to take. They're numbered 0 through the number of courses -1, so if we have 10, they're numbered 0 through 9. We are also given an array called prerequisites that tells us that we must take one course before another. For example, if we have the pair 0, 1, it means that we must first take 1 before we can take 0. And what we want to do is return the ordering of courses that we should take to finish every course while meeting all of the prerequisites. And if there are many options, we can return any of them. And if it's impossible to finish all of them, we return an empty array. So the first thing we want to recognize from this problem is that we have an implicit graph here. Our nodes are classes, each class, or course, I guess they're called in this problem, courses. And then our edges/neighbors are where we need to do a bit more thinking. So typically, in a graph, our neighbors answer the question, from my current node, which nodes can I get to? For example, if we have cities and we're kind of traversing them with roads, the neighbors of a city are all of the other cities that are directly connected to our current city, meaning we can go directly from our current city to this neighbor city. The same logic applies here. The kind of neighbors are going to be nodes that we can access after completing the current course. So for example, there would be an edge that goes from the 1 node to the 0 node, because it says that in order to take the 0 class, you must first take the 1 class. So neighbors are going to be courses that depend on the current course. So for example, edge 0, 1 means we must take, it means 0 has 1 as a prerequisite. Therefore, there is an edge that goes from 1 to 0. So you can notice these are directed edges here. And that's because clearly there's a direction. If 0 depends on 1, but 1 depends on 0, then we have a cycle, and it's not possible to complete all of our courses. Notice that it is, like they're saying, it can be impossible to finish all courses, meaning we can have a cycle here. Got it. Okay, so we have the implicit graph here. Now, what we want to do is return a valid ordering for all of these courses that respects our prerequisite dependencies here. Now, there's a broader name for this, which is, given some sort of directed graph, find a valid ordering to process all of the nodes such that you respect the ordering of our edges. And this is called a topological sort, or a top sort. And there's a nice algorithm that's based on a breadth-first search that allows us to implement a top sort, and that's what we're going to do today. Now, in practice, this is very similar to rationally how you think about this. So if you were a student and you were faced with this problem, typically what you would do is you would say, all right, what are the classes that have no prerequisites? Let me start with those intro baseline courses, and I'll take those. Then, once I've taken those classes, I would say, okay, what classes have I just newly unlocked? What classes are there that I can now take because I have completed these intro-level classes? Then you take those. Once those are out of the way, you say, all right, now that I've completed these sort of 2 levels of classes, is there a next level of classes that I can take? And you take those, and you just kind of repeat this process. And that's what we're going to do here. We're just going to formalize it on the graph. So I'll explicitly draw this one out here, just the one example we had. Now, we're going to define a concept of an in-degree here. So the in-degree is just the number of edges. Actually, the in-degree of a node, it's a property of a node, is the number of edges pointing into the node. So, for example, in our small graph right here, the in-degree of 1, we'll just represent it like this, is 0, and the in-degree of 0 is 1. It's kind of odd that we're using 1 and 0 here, but that's okay. The point is, the 1 node has no arrows that are pointing into it. It has no prerequisites in the context of this problem. The 0 node has 1 prerequisite. There's 1 edge pointing into it, meaning there is 1 class that needs to be completed before you can complete the 0 class. So in-degree just answers how many edges are coming into my current node. And now you can see we can formalize what I said before. I said we would want to start with those classes who have no prerequisites. So formally, we can say we want to start with courses that have in degree 0. This just means that they have no prerequisites. Nothing is depending on them. Then what we do is we complete each of those classes, and then we have to see what we can do afterwards. So for example, when we complete course 1, since we know that course 0 depends on course 1, we can say that in degree of 0 minus equals 1, right? Because we know one of the dependencies for course 0 is course 1, but we just completed course 1, so we no longer have to worry about that. So what we'll do is say, hey, reduce the in degree of 0, reduce the number of kind of remaining prerequisites that I have to fill by 1. Then we can say if in degree of 0 is now equal to 0, then we can take course 0, right? Because this is saying, hey, if we've met all of the prerequisites for course 0, then we're good to take it. There's nothing remaining. And so this is how the algorithm is going to work. We are basically going to maintain a queue that contains all nodes that have 0 in degree. And what we'll do is we'll remove them from the queue and kind of act as if, all right, I'm taking this class. So we add it to our ordering here. And then what we also do is we find all of the nodes who depend on the current node. And for each of them, we decrement their in degree. If their in degree hits 0 after we decrement it, then we add them to the 0 in degree queue so that we can process them in the same way in the future. With that, I think we can go ahead and jump into the code, and hopefully that'll make things clearer. So I'll start by rewriting this ES6 arrow function syntax. And the first thing we'll want to do is we'll build our graph. I'll pass in num courses, and I'll pass in our prerequisites right here. Now, to build our graph, we have one piece of information that's nice and makes this a little bit easier than usual. And I'm going to build this one generically so that it's not just built for the context of this problem, but actually it works for any graph situation where you have a number of nodes and some edges. What we'll do is we'll create our graph, as usual, and we'll return it in the end. Normally, we do these weird checks that are like, oh, if some node from our edge is not in the graph, then we have to add it and make an empty array. But here we know every node, so what we can do is just say start at node equals 0, so long as node is less than num nodes, and then node plus plus, and we can just say graph at node equals an empty array. That way we don't have to do any of our checking that we've seen before. Now, we'll also iterate over each of our edges, and our edges in this problem are formatted as a node and then the prerequisite for afterwards. So we'll say node and then prerequisite of edges, and we'll say graph. Now this is where you want to pause and be careful. Which direction do we want to do this? Remember I said before, the way we define neighbors is like from my current node, what nodes can I now get to? And so from course 0, like when we take course 0, are we now able to take course 1? No, we're not. You're seeing here that they're saying the opposite. When we take course 1, that enables us to take course 0. So we'll say graph at prerequisite dot push node. This is saying we can go from the prerequisite to the node. So once we kind of fulfill the prerequisite, now that enables us to traverse to the next node. And that should be it. You can see this is a lot cleaner than our typical build graph function, and that is because we have this num nodes right here. Okay, great. Next, what we'll want to do is we'll need to build our in degree map, because we need to know for each course how many, or like what its in degree is. So we'll have a build in degree map function. It's going to take in the same arguments. So it'll take in number of courses and then the prerequisites, and we'll have our build in degree map takes in number of nodes and edges here. Now it's going to be a little bit different. So we'll say in degree map is going to be in an object, return it in the end. In between, we know that, well, we know every node is going to have some value. So we can copy this for loop. For every node, set in degree map at that node equal to 0. Right now, we'll just say everything has 0 in degree, and we're going to update the in degrees as we go. Now, we'll have a similar loop to above. So we'll have a node and a prerequisite of edges. And what we'll do here is we will say, now here. So if we look at our above example, this is our edge, and that's saying from 1 we can go to 0. So you can see this first guy, the first position in our array, that is the node who is gaining some in degree, some inbound edge. So we'll say in degree map at node, the first argument here, plus equals 1. So this is saying, or we can do plus plus, I guess. This is saying add 1 in degree for whoever's at the beginning, because now we're seeing that some prerequisite kind of comes before. It has an inbound edge to the current node. And I believe that should create our in degree map here. You'll notice that this logic is pretty similar between these two. If you want, you definitely could put them in one function. And we actually, you know what, let's go ahead and do that, because it is kind of duplicating the code. So I think it would be better code to write it this way. So we'll write a build graph and in degree map function that takes these two values. And then here we can just kind of move a lot of our code over. So we'll have an in degree map, we'll initialize all these values. Here we'll say update our in degree, and then when we return, we'll just return our graph and our in degree map. And that way we don't even need two functions. Okay. So now we have our graph and we have an in degree map. What we want to do now is get a valid ordering. So we'll have another helper function for this. We'll say valid ordering is going to be build valid ordering. And so that'll take in our graph and our in degree map. And I believe that's all we need for now. We'll see if something else comes up that we need. You know what, we'll pass in num courses as well, because I think it would be helpful to know all of our nodes' values. And now we'll implement our build valid ordering function. So we'll come here, we'll have our num nodes, we'll have our graph, and our in degree map. Okay. And one thing you'll notice is when we're here, it doesn't even actually matter that we have courses or anything like that. This is completely a generic directed graph, and we just want to do a top sort on that directed graph. Now, the way this is going to work is, remember, we want to start by taking all of the classes that we can take. And that's all of the classes who have an in degree of 0. So I'm going to have a queue for that, because that's going to be kind of the BFS queue. And you'll see that kind of shape out as we go. But we'll say 0 in degree queue equals get 0 in degree queue. We'll write a function for this. And that will just take in our num nodes and our in degree map. And this should be pretty straightforward. So what we'll do here is we'll take a num nodes and our in degree map. And we're just going to iterate over every node and add it to our queue if it has an in degree of 0. So we'll have a 0 in degree queue, which will be a new queue, and we'll return that queue at the end. In between, we're going to say for let node equals 0, node less than num nodes, node plus plus. We'll say in degree is going to be in degree map at that node. And we'll say if in degree is 0, oops, too many there, then we can add the current node to our queue. And there we go. So this just gets all of the nodes that have an in degree of 0. Now that that is done, we should be able to start writing our BFS. So we'll have to have a valid ordering. We want this array right here, right? Which tells us the sequence of classes that we should be taking. So we'll create that array here. Now, we're going to do our standard BFS type thing here. So long as the queue size is greater than 0, we're going to remove a node. Oops. We're going to process the node, and we're going to add neighbors. And then in the end, we'll return our valid ordering. So what do we want to do here? We can do node equals our queue.dequeue. Now the process node step we can come back to, or actually we don't even have to. We can do it right now. So when we add a node to the queue, we know that it already has 0 in degree, which means we can take it. So at this step, what we want to do is actually take the class. In this context, taking the class just means marking it in an array and saying, hey, we took the class. So we're just going to push the node into our valid ordering. And again, you can notice that this is generic. Even though this problem is about classes, we're writing this function in such a way that anybody can give us any sort of undirected graph and it makes sense. Or sorry, any sort of directed graph. And all of this code makes sense. Like, we're pushing a node, we're not just pushing a class. And that's nice and reusable. So that's good, a good quality to have if you're writing code in a larger code base where people will be taking advantage of your code. Okay, great. Now we're going to add our neighbors. So let's just confirm. So when we process a node, we're taking the class. We need to say add it to our array. And then basically we need to update all the classes who depend on us and say, hey, their in degree just went down. So that will be in the add neighbor step. Now we can say neighbors is going to be graph at node. And we'll say for each neighbor of the neighbors, what do we want to do? Well, we want to mark its in degree down by 1. So we'll say in degree map at neighbor, neighbor minus minus. This is saying, hey, we just took one of the prerequisites for this class, decrease it by 1. And then also, after decreasing it by 1, it's possible that all of a sudden now the neighbor is a 0 in degree node. So we should check that. So we'll say, if in degree map at our neighbor is equal to 0, then we can add the neighbor to our queue. So we're going to add onto our queue right here. So that's going to be the neighbor. And that way, we will continuously be taking classes so long as we're able to. And that should produce our valid ordering that we're desiring. Now we can come back here, and there's one thing to kind of take care of. I'm going to write the code and then talk a little bit more about it. So I'm going to say, if valid ordering dot length is less than the number of courses, then we're going to return an empty array. Otherwise, I'm going to return the valid ordering. And the reason here, there's kind of 2 points I want to talk about. So they said here, if it's impossible to finish all courses, return an empty array. Well, the way we're going to know that it's impossible to finish all courses is if our valid ordering is too small. It does not actually show us taking all of the courses. And in that case, I'm saying return an empty array. As long as our valid ordering length matches num courses, it really should never be greater. It should be equal to. Then we can return our valid ordering. Now, the question arises, why is it the case that if it's impossible, our length is going to be smaller? And there's a related question that you may have noticed that we didn't touch on yet. As we know, whenever there is a graph that can have cycles, we should be using a visited set. This graph certainly can have cycles. This right here is telling us that we can have cycles, because they're telling us some of these inputs will be impossible to finish. However, the way this problem works, the way this algorithm works, this BFS style topological sort, the algorithm is built so that these cycles actually do not cause a problem in the sense that we have an infinite loop. And the reason is because a cycle basically means that the nodes who are in the cycle can never reach 0 in degree, right? An example of a cycle is something like A depends on B, B depends on C, C depends on A. If you have this cycle right here, nothing you can ever do will get these nodes to be 0 in degree. You can imagine you take B, because you're trying to make A have 0 in degree. But in order to take B, you must have taken C. So then you try to take C. But then in order to take C, you must have taken A. And it's impossible to get to a point where one of these nodes has 0 in degree, because they are all depending on each other. And so, in a scenario where we have a cycle, there will be some nodes who are never added to the 0 in degree queue. And that's why our valid ordering length is going to be too small, because some of the nodes are never added to the queue, meaning they're never added to our valid ordering right here. So this algorithm is clever in the way that it actually already accounts for cycles. And another point I want to make is the only way it can be impossible to finish all courses is if we have a cycle. Because if we don't have a cycle, then we are able to make every node get 0 in degree, and then we're able to add every node into our valid order. Okay, So that's why we're not using a visited set here, because we actually don't have to worry about cycles with this algorithm. So let's go ahead and test this and see if it works. Okay, looks like we've got an error. Build graph and integrity map is not defined. It's probably some sort of typo. Yep, I did not rename the function here. Oops. So let's see if that fixes it. Okay, it passes this case, and if we submit, yeah, looks like that worked as well. All right, well, that's all for this video, and thank you for watching.